Lakshmi and Pravina get late because of the meeting and there's Abdullah. General comments? Yeah, Abdullah is here. Any general comments anyone wants to make?
And what's the question? I
Uh-huh.
was drawing a diagram of the direction of the fields.
Yes,
Vector fields, I'm assuming.
yeah, so the idea is that if you have a charge, let's say, moving along this line. Right, so let's say that's your charge. Positive charge moving with velocity v. Right, if it was at rest, we say at a point x, y, z. We know what's the electric field, right? We draw.
Yeah.
The charge to that, but now this is moving around, right? So the direction of the electric field here, what does it depend on? Does it depend on? So this is at time t also, right? At time t.
Okay.
Right. So at time t, the charge was, let's say this is at time t. A little before, it was somewhere here. So the question is, how do you draw the electric field? Is it with respect to this, or is it with respect to this, or is it somewhere else?
Okay.
Right. So this is at time t, this is at somewhere t less than,
Less than T.
so wherever this point is, and be careful with that.
Okay.
Here, when you look at the expression, it will be clear as to where it is. Put in some numbers there.
Okay.
Is that clear? Did I clarify?
And you just figure out what is the electric field.
Yeah, at time t, the charge is here, but probably like this is some past that is affecting you at time t, right? Today is affected by somewhere in the past.
Something.
Like today, if we are seeing a supernova, that probably happened very, very much in the past. I think recently there was a news about how extremely bright, I think they call it what? BOAT, what is BOAT stand for?
Say that again?
There was a recent supernova they found, which was the brightest supernova ever, brightest
Yeah.
of all time, yeah, brightest of all time supernova, I think. They call it both, I think they were not creative at all. So, BOAT, if you look up,
When I Google BOAT super
Nova, yeah.
a whole bunch of yachts pop up.
No, supernova, right? Supernova.
Yeah, but supernova or BOAT.
Yeah, it should. Type GRB maybe. Gamma ray
Maybe
burst.
astronomy. Astronomy.
It should, yeah.
Other brightest ever gamma ray burst.
Yeah. That's a part of it. Mhm. But anyway, my point was that, yeah, if you observe it today, that happened way long back, millions and billions of years back. And then the point is, the direction here, does it depend on the direction at this point or this point? So, and primarily the point is the electric field pointed in this direction or in this direction? But where is the direction?
Which direction?
Yeah, so. At time t, the observation is t, but it happened somewhere from the past. So what's the direction associated with it? Is that clear? Helps.
Yeah. And then we do the same thing for magnetic field.
And the magnetic field. Yeah. Think along that line.
Okay.
How many homework did you post?
How many one?
Homework did you post?
10th is the one that is current going on, I guess. And hopefully today or before Thursday, I'll post 11. And there will be midterm also.
When did you post that?
Huh?
When
Oh,
did you
when
post
will I
that?
post that? Anytime before, let's say, I would say by Thursday or at the most by Tuesday. I worked on it yesterday and I was hoping I'll get something going. But whatever I want seems to be too much. Yeah, so
This Thursday
it's
or
a-
the next?
Oh, surely before, like either this Thursday or Tuesday, at the most Tuesday. I won't delay it more than Tuesday. I'm putting a deadline of strict deadline of Tuesday. Ideally, I would like it to be posted by Thursday.
And how many questions did it have?
I think just one question, one connected question broken into many pieces. Yeah. The easiest would be to pick one problem for the last year, which I removed from the homework and put it. But I'm wanting to do some potentials also. I want to add something to it. But for that, I have to work it out, right? So I am working on the exam if you want. So that's what is slowing things down.
And what subject are you covering for this one?
It will be if a charge is going with uniform speed. It has an electric and magnetic field, and last time I said it kind of folds itself. Like the idea is that if you have a positive charge just at rest, if I'm just looking, so this is the motion, that's the direction of motion. If it is at rest, then this is how the electric field looks like. But as I go faster and faster, these field lines sort of fold itself. So V large, let's say. And there are more lines in this direction. And less lines in this. So this is broadly what happens. Is that here's the folding, so there's more energy that is radiated perpendicular to it than in the direction of motion. And then you can say, in the extreme case, when V tends to be very large, this all the energy will be completely in that plane. And then you have to be very careful of that limit that is all the energy captured in there. Is that even meaningful or not? And the homework problem is to show that actually that solution where everything is on a plane is actually a solution of Maxwell's equation. So Maxwell's equation allows that solution in that particular limit. So it's basically it's like if you have this hands representing electric field, you go faster and faster, these lines fold up, and then in the extreme scenario, they are completely on that plane, which is kind of cool because then you're saying that two charges, one in front of each other, they don't communicate with each other. All the energy is going up perpendicular to that. So it's a non-trivial effect. Then you say, so the classic question you ask is that suppose you have a positive charge and another positive charge. So similarly, they cannot interact with fields now because fields are all perpendicular. But it turns out that the potentials are not really confined on this field. They can actually go beyond that. And then can they interact with each other? And the idea is that yes, they can through this potential. This is closely related to maybe I can say, let's say you have a magnetic, so let's say this is a solenoid. So which means to say that there is a magnetic field that can be confined in a region of space. Correct. So let me change the cross section. So this is a very similar description. Bring it out. That's a solenoid. And let's say the magnetic field is coming out of the boat, so that's B. Is that figure? So that is a solenoid which is confined in space and the magnetic field is coming out of the boat. What is the magnetic field outside a solenoid? It is zero. Right, so that is a solenoid, B equal to zero. Now, what will be the magnetic force on a positive charge here, moving with, let's say, V equal to zero? Velocity equal to zero, what is the magnetic force, Lorentz force?
0.
QV cross V, velocity is zero, it should be zero, right? What about if it was moving? Velocity V. It's still zero, magnetic field is zero, right? There is no, nothing that happened. But now let's say that this goes in a circle. You take this charge physically. And you go around the magnetic field and come back.
It'll produce its own
It will produce what?
its own magnetic field.
Let's say it is slow enough if you really want to avoid that. You were saying there is a current associated with that. But the point is that if you go quasi-statically just to avoid that situation of, or is there anything beyond that? Let's say, even if you're having a velocity that is a current induced due to that. But the point is that, is there an interaction between this and the magnetic field? It seems like there is no force, there shouldn't be. But the idea is that there is an A field here. Even though B is not there, remember del cross A is B. There is an A field in here. And only when you go completely in a circle, if you go halfway, nothing happens. You have to actually go full, right? Then there is a contribution that comes up, which means to say that you have a, think of this the following way, there is a magnetic field, and let's say there is a beam of electrons that you send. Whether you go from this side or on that side, it matters, and you see a let's say a diffraction pattern of this electrons out there. And this is purely a quantum effect. It won't happen if you were to not take care of quantum mechanics. This whole going in a circle and coming back, it won't come in if you don't use quantum mechanics. So that's a feature. So the idea is that even though it seems like there is no force, if you take care of this A effect, the potential effect, remember, A is not supposed to be unique, right? It can be gauged, there is a gauge dependence in there. It should not depend on that. So anything that depends on that usually is interesting. Like, oh, quiz, right? We have not had quizzes for them. So this whole idea is called, I don't know, Bohm effect. And its understanding has like there are challenges associated with that. So, but it's good to be aware of these things that is not within our, I would say, yeah, we can just mention it. A detailed analysis requires a lot more work. In the same way, I was saying, if you have a chart, you fold it up, and the point is that is there a vector potential effect in there, and that's what I was trying to give it in the homework, or just at least give an indication of that. I won't be dealing with anything effect as such, but at least talk about what the potential is. So that's the idea. Does that help?
So-
More than
The charge going around the magnetic field is Aharonov-Bohm effect.
correct. So if you like this idea that if you have a B and you send an electron out there, electron is either going on this side or on that side, correct? So when you come here, it should not see this potential at all. But actually you see a pattern in here. So this is interacting with this magnetic field, even though it is confined within a range. The electrons are not even going there. And you can explain that using the idea that if you go in a circle, they come up. And that's also, remember B dot, so B dotted with to be A, right? What is that equal to physically? Magnetic field dotted with an area, cross-sectional area A, let's say S. What's that called?
I,
Current induced, yeah, you're thinking Ampere's law, but that is if it's a closed surface. But if I keep it an open surface, like closed surface, you're correct, then it is mu Ampere's law. But if I keep it an open surface, that's the flux now, right? Right, so magnetic flux passing through that surface, but we also have del cross A. This is on this surface, and this is dA dotted with del cross A. Right. What is that equal to?
A cross dA.
No, A dotted with dl, right?
Yeah, yes.
A dotted with dl, but now a loop. So the point is that in general, the gauge transformation that we talk about, A is always a gauge dependent quantity, but it is in such a way that the loop integral of A is not a gauge dependent quantity, that's a flux. That's physical. So notice this depends only on A. So here, if you think of A now, the A dotted with dl depends on the flux. There is a flux in this loop. So this quantity can see the flux. That's exactly the flux. So that's physical. So that will always read that quantity. And the point is that can you design an experiment that can sense that? And that's the idea of Aharonov Bohm effect. It doesn't actually sense the A everywhere, but it's the loop integral of A. That's physical. Like this is the basic idea of I think yeah, buried phase, like if you're buried phase will capture this idea again. So that's what it will depend on. Very interesting features can come out of okay. Yeah, let me not say more on it. Yeah.
The charge have to go around to interact with the potential, right?
Not necessarily. For example, this electron goes here, right? So it can go this way, but if let's say starting from here to there, right? Whether the electron goes from here or from there, together that's a difference. Like you can think of this point to this point, the loop is equal to 0. So these two are connected in a sense.
Kind of has a memory.
It has a memory, or one can imagine, yeah, that's the way to talk about it, that yeah, it has the path dependence or the loop dependence. It is not path dependent, it's a loop dependent quantity, topological quantity. Like when you say it is not really dependent on the path, but it depends on whether I've gone in a circle or not, then you say it's topological in the sense. It is not path dependent. Is that clear what I meant? Right. So it's not, yeah. You guys know that. But the basic idea is A is gauge dependent quantity, but the flux, the loop integral of that, it's not a gauge dependent quantity that goes away. It's the basic idea of Stokes' law. Like Stokes' theorem, that's a very basic idea of Stokes' theorem. And remember, Maxwell and Stokes are contemporaries. And Stokes first gave his Stokes, or he used it in fluid dynamics. And immediately within 10 years, Maxwell came up with Maxwell's extension to Ampere's law. So, I mean, it's very natural to think that he was completely motivated or by Stokes' idea in fluid dynamics, but in an entirely different place, and it was revolutionary. Maxwell's equation was significant. Yeah. Okay. So we have homework yet. So that is homework 10. That's due April 13. And midterm, few might be released on April 13. Let's make it due before April 30. Reasonable?
What time is this Thursday?
Yes, I thought so. Isn't that correct?
Yeah.
Yes.
Thursday.
And yeah, because I think we have already covered the stuff needed for it. And it is not very lengthy. I removed the lengthy problem and I'm putting it in the midterm with making it more lengthy. Yes,
The midterm would be due in your mailbox, I'm assuming, or?
yeah, that's,
Okay.
feel free to, I mean, if you feel more comfortable giving it in the class,
Yeah,
give it in the class. If you feel more comfortable giving it in my office, that's also fine. If you ask me, no, I don't care which one. If you ask me, put it in my mailbox. But since you have had, I have cushioned you. Oh, no, I did not receive it. So if you feel any fear
I
of
was
that,
wondering, like, in case, like, I turn it on like a day that isn't on a class day, so.
that should be okay. Yeah, no. Yeah, in mailbox is good enough. Even this is approximate. If you think the April is very pressing, May 1st is good enough, but let's not make it too far. The more I get relaxed, I think you guys will take it. So let's say, remember how about this? We don't have strict exams, right? So I'll provide the submission dates. So be prompt. So let me not make any. Yeah, let me not say it. I think you guys are good.
What was the quiz here?
Oh, quiz. Check out what is Arnav form. Just see what it is and write 2 lines on it.
Have you seen this effect in the lab?
Ah, good question. Look it up, quiz. Let me not make a statement. Like, it's, many people say it has been. Very fixed. So, I think. Yeah. I think, I would say. Yes, there are physical effects associated with it. Now, has it been seen in the lab and in the very strict sense? Sometimes you say direct and indirect, right? So I would say it's considered genuine. But again, I've noticed that it gets controversial very quickly. Concept, let's be just stick to the concept.
Yeah.
So there's a quiz too, has it been asked in the lab or not, right? Has, I don't know, form effect been observed. Yes, I think so.
You should read about it in the books. I've never seen an experiment to
Yeah,
see
I
the
know.
results.
And yeah. Especially where you are from, I think this is very significant. That's not pretty sure. You heard about it. So I'll let you guys make that. I connected with Berry Face and immediately you see the significance of it in a sense.
Have you decided anything about? Have you decided anything about final?
About what?
Final.
Oh, final exam also will be take home. And maybe one question, just so that you guys work on one question on that, which is very simple, and just for the sake of it, so that you guys prepare for it. So there'll be one question. Do you understand? I think, Maz, you have not taken a course with me before. So what I typically do is that if I make, let's say, 80% of the final exam take home, which is a crucial part, and 20% will be just a very small question, which can be, if you just paid attention in the course, you should be able to do it within 5 minutes. Something very straightforward and simple. Like what's the Green's function for, what's the connection between Green's function and potential with a point charge? These kind of stuff that, which is very, if you've done all the homework on your own, then you should be knowing. It's something that played an important role. The homework book was a very small element.
Would we be able to use a cheat sheet in case?
You don't need sheet.
Yeah, okay, yes, yes, you can.
In case I forget.
Yes, you can. Yeah, okay.
For last semester was classical, I remember it was just inverse of a matrix,
Yeah,
2 by
something,
2 matrix.
exactly. Something that is, you've used it again and again, and
Well, in that, I guess, yeah.
Oh, it's really.
but
Green
since you have not
function,
seen the course, it is
Yeah.
understandable that you'll be overwhelmed and you're trying to be prepared with an equation sheet, but I mean, I'll ask a question which you really don't need an equation sheet or anything. If you just worked on the homework on your own, that should be sufficient. I think. Yeah. Something straightforward. And not even tricky, something really straightforward, not even tricky. That's what the idea is, to make you guys work for the exam. And 80%, yeah, I can ask you a very broad, big question. Okay, half an hour of logistics. But okay, let's come to. Yeah, so we got the Green's function for dynamical situations. We said it is so the Green's function for, so we're doing radiation fields. Fields, what are radiation fields? Anyone have an idea of what is typically meant by radiation fields?
Photon.
Photon? Yeah.
Magnetic spectrum. Different
Gamma ray.
lasers,
Yeah, in gamma ray radiation, usually you say that. Let's make it a little more precise.
Alpha rays.
So, how what?
Alpha rays. Beta rays.
Alpha, oh, alpha rays.
Yeah.
Oh, yeah, alpha rays and beta rays, yeah. So if you have a positive charge, it creates an electric field, right? Is that a radiation field?
yeah, just goes out.
It radiates.
So just goes.
So what's the difference between suppose I keep a positive charge here and measure the radiation, let's say at this point on the table, and versus let's say a radiation field, or is it the same or not? That's the question.
I guess.
Doesn't a radiation field has to relate to the speed of light?
No. Notice that electric field goes as 1 over r square. Right, 1 over r square. And energy would be electric field square. That will go as 1 over r raised to 4, right? Because square of the electric field, 1 over r raised to 4. Usually, if you were to capture the energy completely inside a ball, the surface area has r square in it. Right. So as you go farther and farther, your dome has a surface area that is r square. Energy is 1 over r raised to 4. So as you go farther and farther, it really decays off. Energy per unit area that is striking on it, it is really decays off. So the electric field due to a point charge will really go away very quickly, and it will be 0 on the surface of a dome. at the edge of the universe, if you want. So if you would like to have something that survives on the edge of the universe of something that you do here, what should the dependence be?
R.
1 over R, right? So electric field was 1 over R square. If you could think of a field that is only 1 over R, right? Then when I square it, because energy is squared quantity, it will be 1 over R square, and that would survive out there. And the question is that possible? Like, can you do something here and actually let the energy survive at the edge of the universe? And for us, the edge of the universe, what we mean is that when you have a small atom in a sample in your lab, that's at the center, and we observe it about 1 meter away or even 1 centimeter away. That's happening at a Armstrong level. Armstrong and 1 centimeter is infinity, practically infinity for our purposes. So can you do something inside the atom, an electron moving around? Can it do something so that we see the effect at 1 centimeter level? Like, it doesn't die off, but in fact it survives at a very high large radius. And those are called radiation effects, where even at a very far distance, you still have an effect that survives. Even if you enclose it on the dome, it actually survives. Okay, so that's radiation fields very far away that survives. Is that quite clear, at least as a motivation level?
You want to find something is 1 over R, so the energy is 1 over
R square,
R squared.
correct.
How about 1 over the square root of 2, the square root of R, so the energy will be 1 over R.
Then it will diverge, right? Good point. If you have such a field, then it will diverge in the sense as you go farther and farther, you're getting more and more of it, right? Because it is larger. So then it is divergent, which is possibly not. Think of it, is it our quiz, right? Is it possible to have a source or an electric field that is square root of R, and it grows as you go larger and larger? So probably you will have to put in more and more charge. My guess is that if you want to generate such a field, you will have to put in more and more charges. As you increase your volume, you have to create more and more electric field. Just by having one charge, you won't be able to do it.
But the energy will decay.
Energy will grow, right? If you put 1 over square root of R,
1 over
1 over R, and then the area is R square.
R squared.
So it grows, right? So the only way that is possible is that you put in more charge. So you have to put in more electric field, and that won't be physical. But here, what we're saying is the charge should be concentrated in a small region, but still you can get some energy. And we'll do some simple configurations, and from our Green's function, it will be a straightforward calculation. It will come out to be an approximation, in a sense, a very good approximation where you can actually work out the details.
So the quiz is the possible way the electric field is.
Yeah, so the way I motivated is that electric field, so statics, right? Statics is electric field is 1 over R square. So energy is E square is 1 over R raised to 4, and on a dome, so this is R square d omega, right? So on a dome means on a surface area, so this is E square is approximately 1 over R square, right? 1 over R raised to 4, 1 over R square, so that's 1 over R square. So as you go farther and farther, it really decays. Exactly. So that's statics. And radiation in very simple terms is we are talking about electric field 1 over R. Electric field square is 1. Oh, I meant, sorry, that could have confused. Square 4, 1 over 4, that's 1 over R square. Sorry about that confusion. Here, 1 over R square. And when you collect the energy on a dome, this is a constant. it is a distance dependent, independent concept. Yeah, I can get as far as I want, and I still will have some, as far as I capture the whole thing, will be an angle dependent concept. But Aryan was pointing out, what if I have, so this is a quiz, right? The quiz is, what if electric field was 1 over square root of R? Then E square is approximately 1 over R. And this will be square E omega E square will be approximately 1 over R. So that's R, right? So as you go farther and farther, it grows, the energy is growing. And very immediately when I think about it, the only way you'll be able to create this electric field will be to have more and more charges inside as you grow the volume. It won't be easy otherwise to get that. Yeah. Think about it. Yeah.
Okay.
And here our main idea will be, how will you generate this? It will be by acceleration. Radiation is emitted by anything that accelerates, not velocity. If any charge accelerates, it radiates. Is that something that you have heard before? If a charge accelerates, it radiates. What's the challenge with it? This was a big challenge in 120 years back. This is what started quantum mechanics, if you want.
The atom will collapse.
Atom will collapse, and atom has an electron going around it, around the proton. And why do we have the electron going around in a circle? Why can't it just stay there? Right, earlier, that was the idea before 1910, before Rutherford's model. The idea was that there was a positive charge which was a size of 10 raised to minus 10 meters, and electrons were all sitting there on top of it. And that was convenient. But then Rutherford realized that, oh, protons are very small. Then if there is a negative charge, the only way it can be stable is that it has to have a centripetal force associated with it. So circular motion always is accelerating. The only way you can imagine an electron stable inside an atom where the proton is very small after Rutherford model is to have it going in circles like planets. Right? But if it goes in a circle, circular motion implies acceleration. Acceleration implies radiation. Radiation means it will emit energy. If it emits energy, it will lose its energy. Then you would say that, oh, that loss of energy must be very tiny because the atom is stable, right? So the loss you have in one circle, what if it was really, really tiny? Extremely tiny that it is negligible. It's 10 raised to minus 40, let's say. And by the age of the universe, it will hardly lose even 1%, then we are good. But if you calculate that loss of energy, it will lose the energy in a picosecond or probably a nanosecond. So that was not acceptable. Our atoms are very, very stable, right? So how do you save your atom from losing energy? The only way is to make a postulate, right? It is not that you fix that problem using classical mechanics. It's just that we just don't understand it. So we say that electrons cannot go further. So that's the best understanding we have. And that's quantum mechanics, where you make it pretty much a postulate, but I make it very trivialized way that it's a postulate, but seems like we have good reasons to expect that that is what is happening. But the main idea of what I'm saying is that quantum mechanics came up because otherwise atoms will be unstable due to radiation, using energy. Quantum mechanics stops it from happening. So in a sense, does that help roughly? The last part I was.
The electron being unstable.
Correct. That's Bohr's model. Like, why did Bohr come up with a angular momentum quantization? Just so that it doesn't collapse. The atoms or the electrons should not collapse in. Classically, they should collapse in, but they're all stable. So Bohr said that they cannot. That's pretty much what I mean, in a very trivialized manner. It's really being trivialized. Seeing the whole development of quantum mechanics is that you want to stop it, so you just make it a law saying that it cannot happen. That's but there is a lot more. I mean, it's very rich, and the consequences are significant, and it becomes one statement really can explain everything else. and even predict various things. So it is more than just a saying that it cannot. happen. Okay, helps.
It happens, but we don't know why. It happens.
Yeah. So, yeah, good point. Yeah, good point. Yeah, so. Yeah. Okay, coming back here, we said the Green's function, right? Is R minus R prime, T minus T prime is equal to 1/4 pi times R minus R prime. This will be the case if it was static, it's just 1 over that electric potential due to a point charge. That's 1 over that, right? If it was Q, then it is Q over there. But in that, if you want to take care of dynamics, you say that there is retardation. The time is retarded. It's T prime or 1 over C or 1 over R prime. The moment you take care of retardation, you're taking care of dynamics. That's the whole of dynamics being taken care of in that. With that, the electric potential. So now what we want to talk about is radiation is, so you have a region. So this is charges, right? Charges and currents. Again, think of a sample in your experiment. It's in a very small region, atoms if you want, electrons and protons are moving around. That's what here it is, and this is R prime. Like R prime is source. And R is observation, observer. And that's your R. Something is happening in a very small region of space, and observation is made very far away. And that's your R minus R prime.
What is charges?
Charges what?
No,
And
what
currents.
is charges?
Charges and currents. And currents. Okay. So what I'm saying is the charges and currents are confined in a small region of space, and observation is being done in a very far away point from that. So, and that extreme situation will allow us to proceed with our mathematics very easily. So remember your scalar potential and vector potential. So phi of R comma T. Electric potential due to a point charge is simply superposition principle, correct? So it is 1/4 pi epsilon naught. And you add up all the positions of charges, and this time you also add up all the times. And this is dynamics. This is the difference between statics and dynamics. Statics, you have done superposition principle multiple number of times. Now you're doing time dependence also. And not equal. And there is charge, rho of R prime and T prime now divided by R minus R prime. But now your Green's function is not just this, there is a delta function. So there is a delta function of T minus T prime minus 1 over C R minus R prime. This is the additional piece, and that's your integral. You have to integrate over all time. So that's a simple extension if you want. And similarly, currents, how does the currents come in? Because you have the magnetic vector potential also. That's equal to mu naught over 4 pi. Do the same thing, E cube R prime. And this time you have to integrate over all the currents. So that's J of R prime, T prime over R minus R prime. pretty much identical. Like, if you just write it in this form, there you see the connection between the, or the similarity between electric and magnetic effects. This is true for every dynamical situation. There is no approximation being made here at all, except that there was a gauge that was chosen. Like, we worked in Lorentz gauge, and the moment you make Lorentz gauge using the idea of wave equation, you get this. But now we want to say that the moment you say there is a distance r minus r prime, you can think of the total distance. There are two situations that is possible. One is that r minus r prime, let's say the time it takes to go from here to here. This is the time 1/c times this distance. That's the time it takes to go start from the source and reach there. Now, if this is very much small, by doubles less than, I mean very much small, compared to what? Now I have to give you something else. I have to give you a scale. Now, this is a source. Let's say there is a periodicity in it. Something is happening. I have to set a scale there. If it is decaying, how fast it is decaying. So there is a characteristic time tau. So this is the characteristic time of the source. I think of it as there is a charge that is moving up and down. So there is a time period associated with that. But if this is the distance or the time it takes to travel between the observer and the source is significantly small. When is it small? Think of this being very close. Then it is almost instantaneous. That means to say that this is almost zero. If it is less than, very much less than, or equal to the extreme situation, I can think of this is zero, right? If that is the case, then you say it is static and instantaneous. So this is static and more than static and, right? And instantaneous. That's like saying that the supernova happened in, it was 2022 October, and actually the supernova really happened in October, and it almost instantly reached from here, but it has not happened like that. It took a long time to reach there, so that's not the situation. Right, so if it was very much immediately happening, either you could say that it is instantaneous or speed of light is very large, or you're very close to the source. It will also happen if the supernova happened right in our regime, then we will be almost immediately hit, and we will see that on it. May not be that good either, yeah.
Wouldn't it take like 7 to 8 minutes for us to notice the sun if it exploded? Right?
That's correct. It takes about 8 minutes, so 8 minutes to
On your
save you.
right now, it's 8 minutes.
Yeah. So that way Pluto has, if you were living in Pluto, you have an advantage, right? It takes about, how long does it take for the light to reach from sun to Pluto?
Probably
Long time.
A long time is always
not a year though.
comparative to what? Is it minutes? Is it hours? Is it years?
Probably
I think
It's
it's
not
6
years.
times more than 8 minutes.
So that seems, yeah, so that might be correct. So it takes about 6 hours.
Yeah.
Around that time, I may not be, I mean, of course, it depends on whether between Earth and Pluto, I remember there was this they sent a satellite all the way to Pluto, and for every time they send a picture, it took 6 hours to reach us, right? You say hello, it takes 6 hours to reach us. The discussions are very hard. So yeah, in that sense, I remember, so 6 plus or minus, let's say 100% error, 12 hours, right? So it's in hours, yeah. And Mars is
pretty close.
pretty close, and it's 8 minutes to sun. Mars would be,
Like 15.
yeah, it's around that, or and again, it depends on is the Mars on the other side of the sun, or is it on this side of
And
the
also
sun?
planets orbit in elliptical, so
Yeah.
if they're on the shorter side or longer. side.
Exactly, so all that taken into account, so, yeah, later on, hopefully. The way things are going, maybe in decades or so, you might have one of your friends in Mars, right? And then you will have to communicate in the sense, right, half an hour, you say hello and then keep it. So text messages are better probably, there, right? Send it and then you wait for it. So you're already you're getting prepared for communications like that. Yeah, so in a sense, yeah, okay.
What
That's-
we define tau?
Tau is a character, so now the moment I say time, right? I have to compare it with something. I cannot compare it with t because t is an observation time. I'd always compare it with this or some difference in time or a property of the system. So I have to tell you something more about the system. So the best is usually either it's oscillatory. If it is oscillatory, the time period is the characteristic time. If it is not oscillatory, if it is decaying, how quickly is it decaying? There is always a time scale. By any chance, if you do not have a time scale, happens, sometimes happen, rarely happens, then you cannot approximate. So sometimes you will see that, oh, you cannot make this approximation. That's called a non-perturbative regime. Approximation cannot be done because there is no scale. So that's why I was stopping you when you said that, yeah, it's very long, like a long time, but a long time relative to what? So when you say something is small, it has to be compared with something, right? So when I say that this is small, I have to compare it with something. Hopefully you have such a characteristic time in the system, and then it's okay, you're good. Then you just say that as far as I'm very far away, that's good enough. But if you don't have a comparison scale, you often use that, this is the language used, the system doesn't have a scale. And whatever approximation you're doing, then you cannot do. So you have to keep all the time. So then this approximation is not valid, then you're stuck, then deal with the whole thing. And often it is way harder. So often you will see non-perturbative effects are very hard to calculate because you cannot make these approximations. Okay, but we will make these approximations and you will see that it will be significantly easier to proceed. Okay, but that's not for it. So this is static and instantaneous. Static, we have worked sufficiently, so we are not interested in that. So let's take the opposite regime. So 1 over c times r minus r prime is very much larger than the characteristic time. That's what we are working with. But more than that, we are not really working in this regime alone. We will be working in, so radiation zone will be, so radiation, like this is not radiation. Okay? So I want to clarify that this approximation is not what is radiation. Radiation is more like R being, so the magnitude of R being very much larger than R prime, but be more careful, like refer more, right? But I'll clarify this better as I proceed as to what exactly I mean by the approximation. This is not radiation though. This is not the approximation that we are going to make. If we make that approximation, that would mean that I can neglect some characteristic time here. So this will not come in, but we are going to be talking in terms of R and R prime. So let's again concentrate on this. So this is the following approximation. This is what we wanted to do. And it will be such a strong approximation that you will get an answer for this almost immediately. Like this is at this point very difficult to work on. Remember, we are working with a general rho, any charge distribution, any current distribution. I have not specified that this is a charge moving in a straight line or something. So it will be very general. So let's say, I want to say R minus R prime. Let's look at this. R minus R prime. That's equal to square root of R square plus R prime square minus 2 R dotted with R prime. That's the definition. That's what we mean when we write the distance between. This is equal to R. One, let me write this first, so it is 2 times, I've taken an R out, that makes this an R hat. But R out means there's an R square, right? So this is dotted with R prime over R. And it's still exact. No approximation made still. Agree? Remember, let me write it here. Square root of 1 plus x is equal to 1 plus 1 by 2x, right? Plus, what's the next term? 1 by 2, 1 by 2 minus 1 by 2, so that's minus of 1 by 8, I suppose, right? No, 1 by 2 minus
3 by 8.
3 by 8? 1 by 2. Is it minus plus minus, right? It is minus 1 by 2, so it is 1 by 2
1 minus.
and minus 1 by 2, and there is 1, so minus 1 by 8, right? Okay, so minus 1 by 8 x square and so on. I just wrote that for your information. I won't be using that, right? Think of that series. I want to use that to approximate this here, R times 1, and this is minus R hat dotted with R prime over R. And I'm actually dropping anything that is of the order R prime over R square. Is that language clear? Right, this would be, so this is 1 plus 1 by 2x plus order x square. Whatever there is, it is something of order x square. I don't care for the coefficient. But I'm clarifying that I'm neglecting anything that has an x square in it. Okay, here I'm neglecting R prime. So what we are saying is that R prime is very much less than R. So we are in a coordinate system where R prime is all very close. Our observation point is very large in our coordinate system, and R prime, the source, is all within near to that origin. Is that clear? Yeah. Okay, so that's the approximation we are making. So that's good. So that's our R minus R prime. That's this point here. That is 1 in the denominator also. R minus R prime is equal to then 1 over R. And this is 1 over 1 minus R hat dotted with R prime over R. Plus order square, let's say. Okay, if you allow me to claim order square. If I again expand this is equal to 1 over R, 1 plus R hat dotted with R prime over R plus order square. But that's an order square too, so this is 1 over R plus order square, right? If I put the R inside order square, is that clear? So when I'm taking of the denominator, I only need to keep 1 over R. But in the numerator or other quantities, I need to, so the leading order is coming from this piece in here. So put this inside in your potentials. Observation point, time t, that's 1 over 4 pi epsilon naught. E cube R prime, or actually before that I should have done, like first let me go back and do this T prime integral, right? So T prime integral gives me rho of r prime, comma, t prime gets replaced with t minus 1 over c times r minus r prime. Like this is very generic, even before this approximation, I can do this. Divided by r minus r prime. This doesn't require any approximation, this is exact.
How does that happen, like, the denominator part goes to the.
There is this 1 over r, that's 1 over r, right? So second term is r prime, right, dotted with, think of this as r prime over r square. So plus, this is r prime over r square. Agree? Right?
I was asking like, the before step it shows 1 over, right?
Oh, this is, I have used 1 over 1 minus x is equal to 1 minus x square root of minus 1, right? So this is 1 plus x, correct? Plus, I think this is next one is x squared and so on. Okay, so I used that piece in there. And then I argued that I'm interested in the leading power. Remember the radiation field, right? I'm interested in 1 over r, not 1 over r square. Anything r square, it will die away. So I'm not keen on that. So that's it. But again, this does not require exact, right? This is exact. I've not used the radiation approximation yet. But now I use the radiation approximation. Okay. So now I use the radiation approximation, that's equal to 1 over 4 pi epsilon naught. If you are inside the denominator, that's just r, and this is r prime t minus 1 over c times r minus r prime is this, correct? So it is it's r minus r hat dotted with r prime. Okay, writing that more explicitly. With that understanding that I neglected things and divided by r. Right. This is radiation approximate. And we will see more. I'm going to be consistent. Once I have dropped 1 over r square term, I cannot keep 1 over r square ever. Like I cannot drop in one place and keep it at another place. So I've dropped it, so I have to be consistent with that. The big advantage you get in this approximation is that r comes out. There was an r prime in here. This could not have come out. This can come out immediately. And so this is your potential due to a charge, right? But now the charge has to be evaluated at a retarded time. Rho of r prime evaluated at a retarded time. So integral of charge density gives you charge, correct? So that's your Q over R if you want, if you think of it as a potential, this is Q over R, but Q is in the retarded time. So what is TR here? You evaluate it at T minus R over C, right? The observation point, and R hat dotted with R prime over C. That's your radiation potential. Do the same thing for J. Evaluate this, make this approximation, and you learn. So we have retarded time is equal to T minus R over C plus R hat dotted with R prime over C, right? And in that rate, so this is retarded time. This is retarded time. In that approximation where observation point is very far away and all the source points are very close. In that regime, you have 1 over 4 pi epsilon naught times 1 over r times a charge in principle, right? But charge is not evaluated at the normal time. So at a retarded time. You would argue if I integrate the charge density today, I get a charge, right? Total charge in the universe. If I evaluate it at a time in the past, that should still be the same, correct? The total charge should be the same. So should that be the same? Should that be Q?
What was the question?
So the question is, if you have charge density and you integrate over the whole space, right? That should give you Q, right? Total Q. Agree? Why is this not the total Q, or is it the total Q? I say it's not.
Because retarded.
Yeah, but retarded time, it's some time in the past, it's the same number of charges, right? My universe, if I add up all the charges, I should be the total charge, and charge, if it is conserved, it should stay the same. Why should I care? I just replace it with Q. But I say that no, that's not true.
But the chart changes.
Why?
It's moving.
Moving, but still, so what? I mean, as far as I cover the whole, I'm saying I'm having the whole universe. Whether I count it today or 10 days earlier, why should it count?
Maybe
It's
the
because the
distribution.
retarded time is not just in the past, it depends on an R prime also,
Hmm.
right? It's not really a retarded time in the sense of my watch is being backward. And it depends on an R prime there, right? So that complicates the whole point. So, and that's what we have to be careful about. So this R prime, we have to be careful with when we are integrating. Otherwise, it's straightforward. This is just charge. If not for the R prime, like if we drop this,
It's charged.
that's just total charge. It doesn't matter whether I do it at today or 10 days back. And that will be the work we have to do. So what is remaining? Otherwise, it's straightforward, right? So that's the work we have to do. The same thing with potential, right? So this is evaluated at retarded time, vector potential R comma T is equal to mu naught over 4 pi. Again, 1 over R, simple, right? But this is now evaluated about J. Just to emphasize, remember that electric field now, so this is good, right? This seems very straightforward, like R has come out. But what we have to do is we have to calculate electric field. For electric field, we have to calculate the gradient of this potential and take the time derivative of this vector potential, and the magnetic field is the cross of it. Still, it will be coming out much easier. It's just that we have to worry about this dependence. So just in the last 5 minutes, just to clarify how we'll proceed. So let's evaluate. Let's evaluate gradient of phi. Okay. And let me explicitly write this. That means gradient of 1/4 pi epsilon naught 1/r d cube r prime charge density r prime p minus r over c plus r hat. That's what it is. A gradient operator acts on R, right? It has to look for R. Wherever there is the position, that's what it will act on. Where do you see R here? That is there. Where else? This we don't have to worry, that's R prime. This point here, that's R. And R hat also. Okay. So that's the three pieces which we have to worry about. Notice immediately that, so this is gradient of R, right? What is gradient of 1/r? Immediate?
1/r square
1/r square and
negative minus.
and very good. R hat, right? It's electric field, like gradient of potential is electric field, that's R hat. But nevertheless, it's 1/r square. Remember, we are looking for electric field of 1/r nature. So we will note that this is not high enough. But let's see, let's keep going. Let's go here and hit this, right? Notice this is a inside a function, so I have to use a chain rule. Right, I have to use a chain rule, so the gradient of rho is equal to. So I have to do gradient of T of R, right? Think of this as chain rule is like this, right? Gradient of T of R over vector, two steps. This is rho over R, right? If I were to write it like that, use gradient rule d by tr of rho. That involves tr, and tr is nothing but this. And gradient of T of R has this gradient of T minus R over C plus R hat dotted with R prime over C. T does not depend on gradient, so it is minus 1/c times gradient of R plus 1/c times gradient of R hat dotted with R prime. What's gradient of R?
3.
I didn't.
just one.
No. I think what you guys are thinking is this. No. The Lakshmi? R hat, correct? So that's equal to minus R hat over C plus 1/c. And this has this feature that this will come out that this is 1/r. Right? Or you have to worry about that. We'll see that more. This is R hat, right? Already there is a 1/r in there. This is what contributes. This is the important piece in the radiation. This will come out to be higher order. This is already higher order. We will be able to get rid of it. This is the piece that will contribute. We'll come back and work on that. And at this point, we'll stop. So we have the potential, but now we have to calculate the fields. And it will be a very generic field if the radiation fields have a property, it has the electromagnetic wave properties that the magnitude of electric energy is the same in electric and magnetic pieces. Thank you.